And so our next speaker for this session will be Jovan Stojanovic, who will talk about machine learning with dirty data. Tables.
Thanks. So yeah, hi everyone. It's a real honor to be here. So my name is Jovan Stojanovic, and I work at INRIA, which is the French Institute for Research in Informatics. So I work mostly on machine learning with dirty data, but I'm also a maintainer of DirtyCat, an open source project that is linked to machine learning with dirty data, and this is why I wanted to present it to you today. So the question you may be asking is why machine learning with dirty data? Actually, we realized that one of the biggest problems when you're not working with synthetic data, which is maybe most of the time in industry, is that your data is dirty, that people really don't know how to solve this problem easily. Usually it's about cleaning, and this takes a lot of time. So yeah, basically data scientists identify this as the main problem. So we thought actually that there were no adapted tools to resolve this. So we decided to have some of the add some of the solutions that I will present a bit later. But before, I want to just define what is dirty data. So dirty data can be literally, I think, anything that may go out of the collection process. So I've given here an example of how you can write Paris in 6 different ways. You can write it with a typo. So you can write an abbreviation of Paris. You can specify that it's in France. So maybe this is not incorrect to write Paris, France, but it's an alternate version. You may have missing values. So basically, dirty data can be anything. And what we were focusing on is how to do machine learning with dirty data. So how to represent this data specifically for machine learning. So this is why we, in the team, people decided to create DirtyCat, which was an open source project initiated in 2018 by Patricio Cerda, who was a PhD student at the time, and Gaël Varocco. And so the focus now of DirtyCat is on 3 things, basically. Encoding dirty variables, joining tables on dirty data, and cleaning the data, which is obvious. So I'm going to have a demo just like the 3 previous presenters. So if you want to follow, you can go to my GitHub repo or scan the QR code. So yeah. I hope it's OK. Just going to go into presentation mode. OK. So, yeah, hope you can see it, yeah. The first thing to do, of course, is to install DirtyCat if you don't have it from source or from PyPy. And as I am a data scientist by training, so we need a problem. Actually here we have a data set which comes from Montgomery County, from the United States, and it has around 9,000 employees from the Montgomery County. We have some information on them, which is the gender, the name of the department in which they're working, the year in which they were hired, and so on. And so in this case, our machine learning goal will be to predict their wage. So this is what we will use as an example to show you why to use DirtyCat. So basically, the first problem that you have as a data scientist is that you need to encode your variables, because as an input for machine learning models, you need to have numerical numbers. You need to have numerical variables. So basically, you have a dirty column, and you need to represent it with some numbers. So this is an obvious problem. There is this obvious problem in this example would be to represent this column here, which is the job title column, into numerical data. So you see we have some similarity here between job titles. We have different types of firefighters, different types of social workers in our data set. And what it was usually done before actually we introduced this package is that you would use a one-hot encoder. Maybe you would clean the data beforehand, but this may take you 5 hours or even 5 days, depending on the size of your data set. So the output of this one-hot encoder would be something like this. So you know, a one-hot encoder gives a 1 if you're in this category and a 0 if you're not. So it creates a lot of new columns because you add 1 new column for each category, and then it says 1 if you are inside that category or 0 if you're not. So the problem with the one-hot encoder, and you can maybe see it already here, is that our firefighters here are as distant from our social workers as they are from other firefighters. But if you consider the fact that maybe a firefighter has a firefighter 3 here has a wage maybe more similar to another firefighter than a social worker. So this is something that maybe you would want to incorporate into the information you would want to incorporate into your model. So one other problem is that you may have rare categories, so maybe a category with a typo, and in this case, you might not have this category in your test set. So this is another problem of using directly just the one-hot encoder, which is typically what data scientists do in this case. So this is why was introduced actually the similarity encoder, which is an encoder that basically generalizes the one-hot encoder. So it does the same thing as the one-hot encoder, but it takes into account the similarity. So in the numbers here that you see, the encoding, you would take into account the similarity between categories. So you would see that a firefighter here would be near another firefighter, but would be far away from the social workers. And equivalently, social workers would be quite closer here, so closer to 1 in this case. So this is what does the similarity encoder, which was implemented into DirtyCat. And so how does it do this similarity? Actually, it uses the n-gram similarity, which is decomposing the substring of the categories, and then using their morphological similarity to establish a metric. So we saw that it even has better results than typically used, in this case, Levenstein or Jarrow-Winkler methods of establishing distances between strings. So yeah, it works really well. But one of the problems with the similarity encoder is that it keeps the dimensionality of the one-hot encoder. So if you see here, we have the same number of new columns as in the one-hot encoder. And so we have another encoder for this problem, which is called the gap encoder, which actually is an encoder that allows you to specify how many columns you want to have as an output. So this is the n components parameter here, and it actually divides your column into topics. So here, it divided my column into 10 topics, and it gathered some categories together. And basically, the numbers, the encoded categories that you would get in the end would be, activations of these topics. So the topics are down here. The categories are on the left. And you have some kind of numbers which represent the topic activation of my categories. So you see that firefighters are especially activated in topic number 2, which has firefighters, rescuers, and that social workers are more activated in another topic, which is managers, school, and so on. So you see the numbers here actually differentiate between different categories, but also consider which categories are more similar. So this would be important also for our machine learning task further on. And the third encoder that we have in DirtyCat is called the Minhash encoder. So the main advantage with this one, okay, it's completely uninterpretable because it uses the Minhash function, so it's hashing. So maybe the numbers seem uninterpretable, but actually it uses in the same way the n-gram similarity to represent categories with numbers. So you see here a senior supply technician is actually the number, the encoding number of the senior supply technician is actually an intersection of the subwords inside. So the supply, the technician, and the senior subwords. So the main advantage with this encoder is that it's super fast. It's extremely scalable with huge data sets. So I would definitely recommend using actually this encoder. Okay, so we're doing machine learning, so we want to create a pipeline in which we are going to try to predict the wage of our workers. So what do? We use a one-hot encoding on some of the columns, the gender column that we consider as clean, so okay, maybe there's no problem there, the department name column and the assignment category column. We will use different methods for the job title column, just to see how it performs. And finally, so we will use a hit gradient boosting regressor from scikit-learn to make a prediction, okay? So let's look at the results, the most interesting part. Okay, so it's here. So actually, can I have everything? Okay, actually, we can see at the top figure that the dirty cat encoders really outperform in prediction score the one-hot encoder. Why is this? Because we have taken into account, as I said before, the similarity between some job titles, the similarity between some categories, and so as you can see, it has really a huge impact. So the question is, this is why maybe it's not a good idea to clean your data as well, because you lose this information. Maybe with cleaning your data, you would join a lot of categories, but you will lose the fact that there are maybe different kinds of firefighters, which is included with these encoders. When it comes to time, so we can see that the Minhash is really the most efficient way, the lowest computation time here. So I would definitely recommend to use it because it has good results and a really small computation time. So yeah. If you so you saw this huge actually pipeline that I've created here with the column transformer. If you don't want to do this, it's super convenient because we have added for this reason a table vectorizer, which is a class that basically does all of this encoding automatically for you. So you just need to call into your pipeline, it's 2 lines, so you just need to do this, to call into your pipeline a table vectorizer and the model you want to use, and you would have the same results as previously. And you can look at what the table vectorizer did further on using the transformers attributes. So here it basically did what I did, but it used, as you can see, a gap encoder instead of the Minhash, which I used. And it literally divided my columns into 2 parts. So low cardinality columns, which he encoded with a one-hot encoder, which is good, and the high cardinality columns, which you suppose are usually the dirty columns, because dirty columns usually have a lot of cardinality. So he used a dirty cat encoder. And so we had a R2 score of 0.92, which is really nice. So yeah, that's on encoding, but we realized that actually as a data scientist, you have some other things you want to do when you're doing when you're working on a machine learning problem. And one of the biggest problem was actually joining tables on dirty data. So you would want to incorporate more information, to add some more information into your initial table. How would you join on dirty data? So I have another table here, which has information on workers from Baltimore, another county in the United States. And I want to join this information with my previous table, which contained information from the Montgomery County. So how am I going to do it? I'm going to do it on the job class, the job title column that I have in the 2 tables. So if I do a pandas merge, which I would do a few years back, and which most data scientists would do, actually I would get no output at all. because there are no direct correspondences, exact correspondences between the two tables. So this is a problem that we had, and we realized that we needed to do something for dirty data. So we implemented what is called a fuzzy join. It allows you to join your tables on imprecise correspondences. So you see here, he joined my table on different job titles. So this is from my first table. This is from my second table, and so it joined my police officers here with a police officer from the other table. But I don't have a direct, exact correspondence, and this is why pandas merge did not work. So actually, this fuzzy join is also based on the n-gram similarity I described previously, and allows you to join directly. So you may ask, yes, but in this way, I can have some really bad joins. This is why we introduced the matching score parameter, which tells you if this is a good join or not. So 0 is really bad, 1 is an exact join. So 1, if you have 1, you would have a join also in pandas merge. And okay, let's take a look maybe at some of the worst joins that I did here. So I actually joined a locksmith with a property location supervisor. Okay, that's horrible. So I want to get rid of this, and which is good. In fuzzy join, we have a parameter that can allow you to do this, which is called the match score parameter. So just say, okay, above this threshold, I don't want to have joins because my joins are really bad. So you specify a match score, and all of these joins, which were pretty bad actually, are going to be excluded. So you will have missing values instead of this, or if you want to exclude them completely, to remove them, you have also an option for this. Okay, so we have our bigger table, but you may ask, maybe I have a lot of tables. Maybe I don't have only 2 tables I want to join, okay? So I have here a population table maybe. I have a minimum wage table, and I all want to join them together. So how can I do this? We actually implemented a new class to do this, which is called the feature augmenter. The feature augmenter is something which you can directly plug into your pipeline, which is super convenient. It's scikit-learn compatible, so it's really convenient for machine learning. And it actually, you actually specify at the beginning on which tables you want to join, and what is your common join key. So here, the common join key is going to be the year, because, okay, I have my population with a year, I have my minimum wage with a year, and I have my table. If you remember, I had the year when the persons were first hired. So I'm going to join them all using this pipeline. So it's 3 lines. The first line, I'm going to join all my tables. Second line, I'm going to encode them, table vectorizer, which I showed previously. And in the third line, I just add my model. So, okay, I can directly launch it and see what is the score I will have here. So it's a bit better than before. And this was the idea, because we added more information into the problem. So yeah, this is another issue that we were confronted as data scientists, and that we resolved with the Dirty Cat package. And finally, a third, I would say, problem is that, okay, you may have some data scientists, and we had some, which still are asking about cleaning their data. So it may be interesting to still clean your data. So we recently actually introduced the duplicate function that allows you to, okay, clean completely your data, and it's especially meant for typos. So it's actually, again, a one-liner. So you import from Dirty Cat deduplicate, and you deduplicate. I've chosen the column that we saw previously. You deduplicate the categories from the column. So you see here, this method is basically works with hierarchical clustering. So it basically clusters similar categories together. So we basically here joined all the firefighters together and all the social workers together. This is the idea of this deduplicate function. But I would say in the end that you may have to beware sometimes of this function, because actually we realized that without cleaning your data, you might have better results actually for your machine learning problem. So this is good for getting back into the one-hot encoder use case, but I still think that encoding your data properly, if you're doing a machine learning problem, will work much better. So yeah, that's basically all I had for the demo. Yeah, so just to tell you that we have really an exciting period ahead because we're basically evolving this package. It's really growing because we started from like really encoding dirty categories. Now we're working more and more with tables. So we're going to even rebrand the package, which is going to be called Scrub. We will try to include semantics also and other information inside the similarity of the categories. So you might wonder, like, how would language models, which are quite popular today, work in this case? And also, we would like to work in big settings as well. So we will try in future evolutions to work with a lot of tables and really big tables, so inside big databases. So thank you, yeah. You can check our docs. We really work a lot on the docs, so please, if you're interested, check our docs. We have great notebooks with examples of how you can use DirtyCat. And yeah, so this is an open source project, so of course you can contribute and support us on GitHub. Thank you.
Okay, thank you. Any questions?
How do you do with auto joining? Like, you have a table of 20 columns, 20 columns, figuring out the best columns. Do you do anything along those lines?
Yeah, that's a very interesting question. Actually, we don't...
Sorry, could you repeat the question?
How do we do with automatic joining? So basically identifying what are the right joins, what are the right columns on which to join. So currently, we're not able to do it, but this is one of the things I mentioned here, so identifying potential joins among candidate tables. We have some ideas, especially in the database community, they have some ways of doing this, but we're still exploring what are the possibilities, because from the ideas that we tested currently, it's not really working well, so there's not really a method that allows you to solve this problem easily. It's quite a complex problem, actually. Thanks.
Thank you for the presentation. How to find the optimal number of components for the gap method and Minhash method? Do you have some heuristic to find the optimal number of components?
Okay,
or do I need to tune it?
I don't have, actually, from practice, we would need to have more cases to understand better, because these are new encoders. But from practice, I would say that for the Minhash, there is no big difference between how many components you add. This is something from practice. For the gap encoder, you might have a logic there, because you might have actually dividing into different topics, divides your data in a way, you need to have a logic maybe in a way that here maybe the topics need to be close to each other. So if you have too many topics, you will again differentiate some of the categories which are similar. So basically it's an unsupervised problem, so I don't have a definite answer. It depends on your use case. But you really need to look at the data and figure out what's best for you. Yeah. Thank you.
Other questions? Okay, thank you. In this case, next is the coffee break.